Assalamu alaikum, dear students. We are going to study mathematics of FSC part 1 and its unit 8. Unit 8, the topic being taught here are: first is mathematical induction, and the other one is binomial theorem. These two topics are being discussed here. So let us talk about mathematical induction first. What mathematical induction is? So before studying what the mathematical induction is, we will talk about who brought this idea, and then we will talk what is it used for. We will begin with an example. And first question is, who started it? So answer is Francisco Morolico. Francisco Morolico devised method of induction. What did he used it for? He used it for, he proved n square is sum of first n positive odd integers. So first n odd integers, the sum of first n odd integers, first and positive odd integers is n square. He proved it. He presented, Francisco Morolico presented many properties of integers and proved some of them with the help of mathematical induction. So students, the credit goes to Francisco Morolico, who first proved n square as sum of first n positive integers. Then he presented many properties of integers and proved them using mathematical induction. In order to know what is the importance of mathematical induction, first we must know a rule about a mathematical induction. So rule to prove any statement, disprove any statement is to find a counterexample. So we will write here that we are aware of the fact that to prove, in fact to disprove a statement or formula, we require, or all we need to find a counterexample. If a counterexample is found, then the statement or formula will be disproved. Now with the help of this rule, that to disprove a formula or statement, we will come to know that why we are using mathematical induction. So we are now turning towards the reason why we are using mathematical induction in mathematics, or what is it used for. So now we are aware that counterexample will be required to disprove any formula or statement. Now we consider an example. Example is found by or presented by Euler, another renowned mathematician. Example is this statement. Statement is denoted by S of n. What SFN states? SFN states n square minus n plus 41 is a prime number this is a prime number for all n belongs to natural number. It means whenever we will substitute a positive integer, that means a natural number, this formula n square minus n plus 41 will give us an output a prime number. This is what we are going to discuss now. This will help us to know why we are using mathematical induction. Now we talk about this example found by Euler, a very well-known mathematician. So in order to check this, we form a table here where inputs are natural numbers. Output, let us see what the outputs will be like. So let us take input from set of natural number and output S of n will produce natural numbers substituted here. From the first choice, we know that first natural number here is 1. We are going to substitute from 1 onward. 1, 2, 3, 4, 5, 6, 7, 8. And we keep on substituting 9, 10, 11. So what numbers we are going to obtain from this formula n square minus n plus 41. When 1 is substituted, you can see both 1 will be with opposite sign, so answer is 41. Then for input n equal to 2, output will be 43. For 3 it is 47. For 4 it is 53, 61, 71, 83, 91, 113, 131, 151. This is 131 and 151. These are the numbers. All numbers here we can see. Outputs here are prime numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We keep on substituting values. We find output 41, 43, 47, 53. We know all these numbers 41, 43, 47, 53, 61. All these numbers are prime numbers. 91 is a prime number. Everyone knows 113, 131, 151. These are prime numbers. So when these are prime numbers, then we can we talk about the above statement which claims that S of n, where n square minus n plus 41 is a prime number for all natural numbers. When we substitute these 10 prime numbers, 11 prime numbers, we always find a prime number. When we substitute these natural numbers, we always find these prime numbers. It means now we write statement, kind of a conclusive statement about this table statement and corresponding table. We can write conclusive statement. What that conclusive statement is, it's not the final conclusion, but we are trying to make a conclusion from, we make an observation. That observation is the above statement has enough chance of being true. Enough chance of being true because whenever we substitute a natural number, it gave a prime number, which is the statement of claim of the statement also. It means statement can be called true, but let us know another rule of mathematics. Mathematics says mathematics talks about them or calls these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 41 to 151 or even more. Mathematics calls them specific cases. So what the rule is, these are specific cases and this is general rule. General statement. General statement says it is a prime number. General statement says it is a prime number. And in particular cases, we find prime numbers. So when we find prime numbers, then we can say it is generally true. It will always be a prime number. For this we have a rule. What the rule is? From these specific cases, we cannot deduce this general statement. From particular cases, we cannot derive general result. Remember, this is mathematical rule. We cannot derive general result from particular cases. So what particular cases and what is general rule? Let us see it again. These are particular cases. When the value of n is 1, value of n is 2, value of n is 3, value of n is 11. These are particular cases. In particular cases, we found these prime numbers. So from these particular cases, we cannot refer to this general statement. We cannot conclude this general statement that this is always a prime number. We cannot say, because when we say this is deduction made from these particular cases, when these particular cases every time we found a prime number according to the statement says it is always a prime number when natural number is substituted. It means from these particular cases there is a chance that we can go, but mathematics restricts. Mathematics says particular cases cannot refer a general result. Now we require, how can we test the above statement? It involves many calculations. Now the question arises, how can we test the validity of above statement? How can we check the validity of above statement is the question. Now here is the solution. Here is the solution. Solution is formulas are statements. Formulas are statements associated with natural number set. With this statements natural number set, right? So formulas are statements associated with natural number set, can be tested, can be verified using mathematical induction. So the requirement of the method, now we come to know that what is the requirements. Let's look at it again. What does it talk? This is the statement. It claims you will find a prime number whenever you substitute a natural number. We substituted natural number. How many natural numbers? 11 natural numbers we substituted. We found every time a prime number. Now there is a chance that we can say from these particular cases, in these particular cases we found every time a prime number. Now we can say that it is every time a prime number because we have tested it. No. What mathematics says about it? Now we can, above statement has enough chance of being true because every time it gives a prime number whenever natural number is substituted. Mathematics says from these particular cases you cannot go to general result. You cannot say that this statement always produces, this formula always produces a prime number. Mathematics restricts it. Despite of it, in spite of the situation, we have to test that statement whether it is true or false. How can we test the statement is the next question. Can we test this statement, above statement Sn? We can test it. How can we test it? Here is the solution. Formulas are statements associated with natural number set can be verified using mathematical induction. So that is why we use mathematical induction. We cannot find every time a prime number. We cannot test every statement for all values, because here look at it again. We will have to go for this rule, because if we keep on substituting, if we substitute here, put n is equal to 40, n is equal to 41 in above statement. If we substitute n is equal to 41 in above statement, what we get? As a 41. 41 square minus 41 plus 41. Look at it. It will be 1681. Has how many factors? Its factor is 1, 41, 1681 itself. So this is, output is not a prime. But look, how many natural numbers we substituted? What is the counterexample? 41 is counterexample. For this statement, we keep on substituting. We keep on substituting natural numbers. Up to 40, we will always find a prime number. But when we substitute n is equal to 41, we find a number which is not a prime. This fact is against the claim of the statement. Statement is disproved. But are we able to verify? Another question here. Can we test a statement for 40 values? Can we verify a statement for 40 values? This statement can be verified for 40 values. Can be tested for 40 values. Maybe some other statements are verified for 100 values, for 200, for 500, for 1000, for even more values. The counterexample we find after even 100,000 values. Then what? So we are unable to test a statement for multiple values, because it can involve infinite calculations. So it is very much time taking. It is very time taking activity. To verify a statement for 40 or even more values. So we must require an alternate. We require an alternative method of verification of such statements. We have a method. The method is mathematical induction. Method is mathematical induction. And now we will write principle of mathematical induction. What is principle of mathematical induction? Mathematical induction talks about formulas or statements. They are denoted by Sn. So principle is, if a statement or proposition you know that mathematics is subject of symbols. So statement or proposition is denoted by Sn, and that statement is such that means it is of the type. If a statement or proposition Sn is of the type, what type? Number one, S of 1 is true. That is, we elaborate it. When we substitute, the statement is true for n is equal to 1. When we substitute n equal to 1, we find an obvious result. Obvious result like 2 is equal to 2. You cannot say 2 is equal to 2 a false statement. You will always say that a true statement. 2 is equal to 2 is a true statement. So whenever you substitute n equal to 1, the statement formed before you is like 2 is equal to 2, a very much obvious basic mathematical fact. So you will call that true. So when a statement f is such that when you substitute n equal to 1, you find a true result. Number 2. S of k plus 1 is true whenever S of k is true. Now, what this step is about, we have to suppose S of k. We have to suppose S of k is true. On the basis of that, we will prove S of k plus 1 is true. This is supposition. This will help us to prove S of k plus 1. So k, remember that we are talking about positive integers. This is one positive integer and this is next. From one positive integer we move next. We move to next positive integer. Statement for k, statement for next positive integer. So from one positive integer, if we can move to the next positive integer, then we conclude, then we can draw conclusion. This is mathematical induction principle. We can draw conclusion. Then refers to the conclusion made. Then S of n given statement is true for all positive integers. For all positive integers. So conclusion is drawn here. Now, dear students, this concludes who devised mathematical induction principle? Francisco Morolico. He proved n square is sum of first n positive odd integers. So this is exercise 8.1. So what Francisco Morolico did, we are going to do now. Question number 2, look at it. What it states. The statement of the question is that 1, 3, 5, so on. 2n minus 1 is equal to n square. Before starting this chapter, usually FSC students have studied Unit 6. Unit 6 tells us what this structure is. This structure is called series, arithmetic series. 1, 3, 5, so on. This is arithmetic series. Actually, these are first n odd integers. First odd integer, next positive odd integer, next positive odd integer, and this is nth positive odd integer. So these are first n positive odd integers, and right hand side shows their sum. So those students who have studied series, they know this is arithmetic series and this is their sum. How can we find the sum of an arithmetic series? This is we have studied. This we call their A1, the difference is 2, and then we can find this is last term, this is last term, this is first term, both are added. A1 plus an, first and last term are added and multiplied by n by 2 will give us sum which is equal to n square. Very easy to verify, and since that is not our topic here, but we must know what left hand side shows. Left hand side shows arithmetic series with its n terms. Right hand side shows sum of its n terms. We will verify it through mathematical induction principle. So we have 2 steps involved in it. Step 1. Solution goes. Step 1. We substitute n is equal to 1 according to principle of mathematical induction. We will obtain first value of the statement, first value of the statement is, on left hand side we substitute n is equal to 1, we will get this shape which is equal to 1 simplified, and 1 is obtained. Now right hand side is evaluated on 1 gives 1. So left hand side equal to 1, right hand side equal to 1. We can conclude this. Obviously left hand side equal to right hand side implies the statement S of n is true for n equal to 1. Step 1 is completed. Step 1 is first condition of mathematical induction principle. Whenever a statement is verified on n equal to 1, it must be true. So we can find left hand side and right hand side both are equal. It means the statement is true for n equal to 1. Now we move to step 2. What the step 2 is? We talked about step 2 while discussing mathematical induction principle. What is step 2? Step 2 is supposition of S of k. We suppose S of k is true. What S of k is? That is, we now write that what we consider, what we suppose true. We suppose S of k is true. Now we will write what S of k is. So this given S of n is now transformed into S of k. Only the change of variable takes place here. 1, 3, 5, so on, 2k minus 1. These are n values of this series. These are k values of this series. Only variable is changed. N variable is used here, k variable is used here. This is equal to n square, this is equal to k square. Entire statement, given statement, is transformed in k variable and is considered true. This is second condition where we suppose S of k is true. In second condition of the mathematical induction principle, we consider the S of k statement for k values true. Now we prove. We have to prove. S of k plus 1 is true. We have to move further to the next positive integer from this one. This is kth positive integer, and we have to move to next k plus 1th positive integer. We have to make a statement for S of k plus 1. If this statement is transformed for S of k plus 1, for k plus 1 values, what it will look like? S of k plus 1. This is 1, 3, 5, so on, 2k minus 1. How many values these are? As we know here, these are same values written in the previous statement and this statement again. These are k values. These are k values. Now we move to k plus 1 values. If we substitute in it 1 for value of k, 1, we get this first value. If we substitute 1, we get 1. If we substitute 2, it becomes 4 minus 1, 3, second value. If we substitute 3, it gives third value, 5. If we substitute k, this gives kth value. This is general value. Now we substitute k plus 1, it will give us k plus 1th value. If we put k plus 1, it will become 2k plus 2 minus 1, finally 2k plus 1. And look at it, what this statement is. We must look at the first statement. What the first statement is? These are n terms of the series, and right hand side gives sum of these n terms. N terms of the series, right hand side gives sum of n terms. What is this statement? This statement is k terms on left hand side, and right hand side gives sum of k terms. And what it must be? These are how many terms here? How many terms? These are k plus 1 terms. If we can rewrite it, 2k plus 1. These are k plus 1 terms. Right hand side must show k plus 1 terms sum. So k plus 1 terms sum is given by this. It is simple, not complicated. This statement is for k values. This statement, these underlined statements, these underlined terms are how many? Same like this, k terms, k terms. This is next term. Which one? This is kth, this is k plus 1th term. And right hand side shows initial statement, right hand side shows n square, sum of n terms. This shows k square, sum of k terms. This shows k plus 1 square, k plus 1 terms sum. Let's look at it now. How will we prove? We have to prove this statement. This is the statement which we have to prove. How will we prove it? We have a method to prove. We can convert this left hand side into this right hand side. The statement will be considered proved. So this is the method we adopt. What we adopt? We start with left hand side and convert it into right hand side. 1, 3, 5, so on. 2k minus 1 plus 2k plus 1. These are k plus 1 terms, but these underlined, look at it, are k terms. Now we know that k terms have their sum, k square. If we can replace all these terms by their sum, all these terms, k terms are added. K terms are added will be equal to sum of k terms. And what is the sum of k terms is given by this statement which we name equal to 1. If we can name this 1. This statement is 1, and now we will use it here. It gives us sum of k terms equal to k square. Now we have k terms here. We can replace sum of k terms by the value k square plus this is k plus 1th term 2k plus 1, and we will refer it to 1. That this change is due to using this 1 which we supposed to be true. We suppose this. On the basis of this we have to prove. Now we started the statement which we had to prove from its left hand side, and from left hand side we can see this part is what we supposed, equal to k square. So that supposed value is written here. This all statement, these all values are replaced by their sum, k square, and this is k. Now what can we find from here is this is k plus 1 whole square. This is right hand side. From left we reached right. S of k plus 1 has a left hand side and has a right hand side. We converted left hand side to its right hand side. It means this S of k plus 1, this statement is proved. This implies S of k plus 1 is true. But remember, we have to write here whenever S of k is true. So this has happened. Step 1, our condition 1 is proved true. Then we proved condition 2. Condition 2 is also satisfied. Now we can conclude. What is the conclusion? Conclusion is according to the mathematical induction principle, and conclusion is that S of n, this is the conclusion, S of n, hence we write conclusion. Hence what? S of n is true. S of n is true for all positive integers. If students, surely you will have mathematics book with you, so you can see that where questions of 8.1 exercise begin, it is written that prove the statement for all positive integers. What we did, according to mathematical induction principle, we verified it for n equal to 1. We found left hand side equal to right hand side, means statement is true for n equal to 1. Then we moved to step 2. In step 2 we supposed S of k. We transformed this given S of n into S of k. This S of n simply is converted to S of k and is supposed true. We name it 1. Then we say that we have to prove S of k plus 1 is true. What is S of k plus 1? S of k plus 1 is to be stated. Here these are k terms. These are k terms. We have to move to one more term ahead. The next term, this is kth term, next term is 2k plus 1. and this gives sum of k terms, this must give sum of k plus 1 terms, which is k plus 1 whole square. Now we had to prove this statement true. This left hand side equal to this right hand side means this statement is true. So we adopted this method. We begin with left hand side and we transform that right hand side. We cannot do it unless we use our supposition. We use our supposition, we transform this left hand side into this right hand side, and then we say that s of k plus 1 is true. A statement whose left hand side equal to its right hand side is called true. So this statement is s of k plus 1 whose left hand side is proved equal to right hand side. So this statement s of k plus 1 is true. When this happens, these two conditions are satisfied. Mathematical induction principle allows us to conclude. Hence we conclude the given statement is true for all positive integers.